For over a century, a single piece of machinery drove the entire industrializing world, the internal combustion engine. But millions of those engines running constantly produced a dangerous byproduct. Thick, suffocating smog blanketed urban centers, and atmospheric carbon climbed steadily. Electric vehicles offer a zero-emission alternative for passenger cars, but lithium-ion batteries are heavy. They lack the extreme energy density required to push a fully loaded container ship across the Pacific or keep an airliner at cruising altitude. To keep global supply chains moving without breaking emissions targets, engineers have to look past the metal. The only way to save the engine is to rewrite the chemistry of what goes inside it. In thermodynamics, the molecular structure of the fuel you burn completely dictates the mechanical architecture of the machine you build. A standard 4-stroke gasoline engine requires a highly specific diet. For every 1 part of vaporized fuel by weight, the cylinder needs exactly 14.7 parts of air to achieve a perfect stoichiometric burn. To extract maximum efficiency under pressure, that fuel has to be patient. An octane rating measures that patience. It's the liquid's chemical ability to resist detonating too early during the violent squeeze of the compression stroke, avoiding a destructive shockwave known as engine knock. Diesel engines take the squeeze to the extreme, shrinking the chamber to a 20th of its size. The highly compressed air superheats. When dense fuel injects, it auto-ignites, pushing the piston down with a slow, steady expansion rather than a sharp, explosive spike. Because they don't need a throttle valve restricting incoming air, diesel engines avoid massive pumping losses, converting steady fuel burn into immense pulling power. By selecting a volatile fuel for a high-revving spark engine or a dense fuel for a compression engine, engineers predetermine exactly how a machine will behave before a single block of iron is cast. Hydrogen represents a totally different extreme. It burns incredibly fast and ignites in mixtures so lean they are almost entirely air, leaving 0 carbon emissions. This chart illustrates hydrogen's primary nightmare, its minimum ignition energy. At 0.017 millijoules, it needs vastly less energy to ignite. This extreme sensitivity means the tiniest hotspot can ignite incoming hydrogen prematurely. The flame front travels backward into the induction manifold, causing a violent backfire. Taming this element requires specialized hardware. Injectors must blast the hydrogen directly into the closed cylinder at extreme pressures, up to 350 bar, while active ventilation systems constantly purge the crankcase to prevent explosive gas buildup. Extracting harmless water vapor from an exhaust pipe demands an engine block heavily armored against its own fuel's tendency to self-destruct. We can build highly specialized engines for the future, but we cannot instantly scrap the billions of legacy engines already operating worldwide. Instead, chemical engineers are developing drop-in replacements like e-fuels. By capturing carbon dioxide directly from the atmosphere and combining it with green hydrogen, they synthesize a liquid hydrocarbon that behaves exactly like petroleum. Unlike early agricultural biofuels such as ethanol, which carries a 33, these synthesized and gaseous liquids function as a critical bridge. They freeze the accumulation of atmospheric carbon while utilizing a century's worth of existing mechanical infrastructure. The era of relying on a single, universal liquid to power everything from lawnmowers to locomotives is over. Heavy global freight will run on energy-dense e-fuels and diesel. Zero-emission industrial sectors will harness the volatile power of pure hydrogen. And legacy fleets will sustain themselves on closed-loop carbon chemistry. The internal combustion engine is far from obsolete. Empowered by highly specialized chemical formulas, it is simply adapting into its most efficient and sophisticated form yet.